Welcome everybody, and thank you for your interest in our paper. My name is Liebers. I am a research assistant at the HCI group of the University of Duisburg-Essen, and on behalf of my co-authors, Patrick Horn, Christian Burschik, Uwe Gruenefeld, and Stefan Schneegass, I will be presenting our work using gaze behavior and head orientation for implicit identification in virtual reality here at this year's VRST to you. User identification measures on state-of-the-art head-mounted displays for virtual reality is a recent research topic and required to, for example, personalize the device. Through personalization, we can, for example, set user preferences within an application or adapt the difficulty of games. Here, you can see the currently widely employed authentication method of entering a password in virtual reality with a handheld controller. It looks cumbersome as it is, does it not? For this reason, we want to explore a gaze-based behavioral biometric that implicitly can enable authentication in VR. Gaze is considered to be a highly unique and individual personal trait, often used for behavioral biometrics. Not only can we use the physiological features of the human eye, such as an iris pattern for authentication, but also the behavior of the eyes itself. The eyes can be tracked with an eye tracker that is located inside a head-mounted display, and they can perform various movements, such as fixations, where the eyes stand still and focus on one point, smooth pursuits, where the eyes move slowly and track a moving object, and saccades, where the eyes jump fast from point to point, for example during a reading activity. We believe that these behaviors are highly unique and individualistic and can be used to identify people. In our work, we want to exploit these behaviors and in particular their associated gaze velocities for user identification. Our core idea is that an immobile stimulus elicits fixation eye movements, whereas a slowly moving stimulus induces smooth pursuits. Once the stimulus moves faster and faster, a smooth pursuit might not be enough to follow it, hence saccadic eye movements are elicited. From a certain point on, it might also be necessary to support these saccadic eye movements by performing an additional head rotation. We hypothesize that the obtained values for the eye movement's velocity, as well as the transition timings and the speed of the head rotation, are highly individual and in fact usable for authentication in VR. We designed a user study to invest this hypothesis. In order to investigate the differences in gaze behavior between persons, we use two dynamic stimuli, each on their own trajectory in virtual reality. Here, indicated in red, is the field of view in VR. The inner ellipse represents trajectory 1 for the first stimulus that stays within these bounds at all times, whereas the outer ellipse exceeds these bounds. Both stimuli increase their speed over time, but as trajectory 2 exceeds the field of view, a head rotation must be induced to follow it continuously with the eyes. To evaluate our work, we conducted a user study in our lab and invited 12 participants, where 2 identified as female and 10 as male. The age span ranged from 21 to 28 years with a median of 25 years. Unfortunately, during the study, one participant encountered cyber sickness, so we stopped the procedure there and remained with 11 complete data recordings. Our study followed a within-subject repeated measures design where we recorded 3 repetitions per stimulus. To do so, we have utilized an HTC Vive head-mounted display and the eye tracker add-on for said device that is provided by Pupil Labs. At first, we want to gain insights into the data and understand if the seeked individuality within the data exists. We do so by employing an explainable machine learning based on k-nearest neighbors at first. In the second part, we will use deep learning to maximize the accuracy. To evaluate our concept, we first collect the participants' data by setting the eye tracker to a resolution of 400 x 400 pixels at 120 Hz. We furthermore perform the vendor's default 16-point 3D calibration routine. After collecting the data, we apply a confidence filter of 0.4 to the data. This filter replaces all recorded data points with not a number markers that indicate that the eye tracker was not confident at the time of recording, as for example it is during blinks. Next, we classify the stream of data into segments where saccadic movements, fixations or smooth pursuits occurred. After we obtain the segments that were classified as fixations, smooth pursuits or saccadic eye movements, we create feature vectors by applying summary statistics, by especially focusing on the mean peak velocity. For stimulus 1, we obtain a 3-dimensional feature vector, whereas we include the head rotation for stimulus 2 and obtain a 4-dimensional feature vector. At last, we classify these feature vectors in an 11-fold cross-validation where we designate one of the 11 participants in turn as an unknown person to be rejected by the system. We utilize a k-nearest neighbors algorithm that makes use of a distance threshold and sets the parameter k to 1. For stimulus 1, we obtain accuracies between 36% and 55% for the worst and best case respectively. In total, we find a mean accuracy of 45%. To the right, you can find a plotted version of the KNN, where the colors denote the participants' data on a log scale. For visibility, we only depict the smooth pursuit and saccade peak velocities, and by the color clusters we can see that there is some inherent similarity within the data. Alike for stimulus 2, where we include the head rotation, we find an overall increase where the best case equals 82% and the worst case equals 73%. In total, we find a mean accuracy of 75%. Since we now saw that there is inherent similarity in the data, we try to maximize the identification accuracy. We do so by utilizing deep learning, which is known for being capable of performing the required feature engineering on its own. In the first step, in terms of resolution, sample rate, and calibration, all values are equal to the previously presented machine learning evaluation. But since anomaly detection for deep learning is a current research topic and the rejection of unknown data samples is as well, we focus on a pure identification scenario where we do not designate an identity to be rejected here. In the second step, we again apply a confidence filter of 0.4. Here, we do not set values to not a number, but perform an interpolation instead, as the deep learning models cannot work with not a number markers in the data. Moreover, we equalize the different sampling rates of our data by upsampling the head rotation data to match the gaze data to fit them into one data frame with no dilation on the time axis. In the third step, we apply a clipping and min-max normalization to fit all values into the range of 0 to 1. Moreover, we apply a pre-padding and make use of the sliding window technique where we set 300 as the window size, which corresponds to 2.5 seconds, and 150 to the stride so that we have an overlap of 50%. At last, we perform a 3-fold cross-validation where we use one recorded sample per turn as the validation sample. We moreover utilize 10 different deep learning model architectures as proposed by VRST et al. In their survey paper on deep learning for time series classification. As a result, we obtain very high accuracy values where the encoder model stands out by a mean accuracy of 97% for stimulus 1 and 100% for stimulus 2. These values are to be understood after the application of the majority vote that operates on the prediction of the single slices created from the sliding window technique. Here we can see the overall determined accuracies. Particularly the encoder model appears to be a good fit amongst others, as the accuracy is relatively high across the board. Yet it needs to be noted that the other models proposed by VRST et al. That are not listed in this table did not converge. So what can we conclude in the end? First, we see that gaze can be used to implicitly identify users. We also find that head rotation overall improves identification accuracy. We believe that these findings can be used for implicit identification where a user just follows a stimulus in VR with their eyes that ideally includes a head rotation. This could be a ball in a spectated tennis or football game or a virtual airplane in the sky. Thank you for your attention.